Okay, guys, it's me again. I'm Manolo. We're going to talk today about weight and balance. So let's get into this right now. Hi, weight and balance. Today, we're going to be talking about weight and balance. And this is part of the second section of the instructor PTS on the technical subject area. And this is task F, weight and balance. And again, the disclaimer here, this lesson is a practice lesson I'm preparing as I get ready for my check ride for my instructor rating. Mainly this is recorded to see myself and see how I performed and fix whatever I need to fix, correct my concepts and things like that. So it's not intended by any means to be formal flight or ground instructions. So don't use it for that purposes, right? I mean, feel free to provide any feedback, but don't use it for flight instructor. Um, um, if you need training, then look for a certified flight instructor or ground instructor, okay? So let's start with this. I sent you, I'm assuming that you guys reviewed the lesson plan I sent yesterday. We're going to be using a couple of references here, mainly the PHAC. A lot of the content on this is coming from the PHAC. Today, the objective is that you learn the main concepts about what impact weight and balance has in performance. We will go over the different and stability as well, and then we will go over the typical methods you will find about calculating weight balance, and then last but not least, we will go into a couple of examples what happen if you need to you have some changes in your weight and how you would find how if you're between balance or not, or a mathematical way to find that faster, right? So this lesson is going to take around an hour. We're going to be using Zoom because we don't have a whiteboard. We're not physically located today. And then um, we might be using a little bit of Excel instead of the whiteboard as well to help you understand the concepts. And then your objective here is that you should have read some of the PHAP. You should have seen the video I sent to you, and then participate, take notes, and answer questions, okay? All right. So how do we know that we have achieved completion standards of these lessons? Well, at the end, you should be able to demonstrate to me that you understand the concepts associated with how weight and balance affect performance, that you can explain to me the different methods that you will find to calculate weight and balance, and then how to calculate shift in balances, weight and balances. So with that, let's go and get into the lesson, okay? So the first thing I want to ask you guys is, what do you think weight and balance is important? Why we need to study? Anybody knows? Go ahead. Okay, cool. Yeah, it is important. The aircraft have to fly between balance in order to can satisfy the design. So let me show you a little bit of an example what happened when we don't are between weight and balance. So let's see this video quickly. I know it's graphic, and I know it's kind of might affect you, it might scare you, but this is exactly what happened if we don't weight and balance correctly the aircraft. In this case, this aircraft was properly balanced before takeoff. For some reason that we will not go into now, the cargo shift, and then the cargo went all the way back, and the aircraft became uncontrollable because the center of gravity of the aircraft was out of their aircraft limits, and it was uncontrollable, as you saw. So hopefully you understand now why we need to pay attention to these, why this is relevant for the safety of our flights and our passengers. And before I start getting into these concepts again, I just want to kind of point out that I think it was last week or the week before, the NTSB also released, it was no accident like this, but it was an accident that happened last year leaving Scottsdale when this Piper was overweight, and also center of gravity was after the limitation of the aircraft. And it looks like the engine was not developing enough power, whatever it was. Of course, the aircraft was not going to fly as designed because it was already out of the design limits. So hopefully you understand this, understand why we need to pay attention to this, why we have to be very diligent on calculating weight and balance and understanding how affect our performance, and more importantly, how affects our safety. All right. So with that said, we're going to cover the first topic today, and the first topic of our lesson is going to be we said we're going to talk about the the impact of weight in performance. So let me write this quickly here, guys, so you can see how that works. Let me share my other screen. Cool. So what we're going to do today is talk about impact of weight. That's the first topic, weight, and is impact on performance. All right. So what happened typically? Let's assume for a moment that the aircraft is heavier, right? If it's heavier, then we're going to have a higher takeoff roll, for example. Correct. We're also going to have a higher takeoff or lift of speed. We are going to have a lower cruise speed, right? Because we're heavier. And also another consequence of being heavier on weight is our endurance is going to be lower. Or shorter, I would say. Then in terms of, just think about landing. If we're landing, what do you think is going to happen? Of course, our landing roll distance is going to be longer. And then also our landing speed is going to be higher, okay? So if we're lighter, then all this is going to be the opposite, right? Performance. All right, so the other topic I want to talk is how weight affects airplane structure. And for that, I will bring quickly again our BJ graph, right? And if you remember our speed versus G graph, you will remember that weight has an impact on load factor, right? So if we're unaccelerated, right, G's doesn't increase. But let's say we're turning now, we're accelerating, right? So as we turn and we turn more, right, let's say we increase our angle of bank, then we're going to have a higher load factor. And then the importance of this, the heavier we are, right, then the higher that load factor it is, and the closer we're going to get to these structural damage areas if we're not careful, right? Typically, some people might have even flown about these limits and the airplane doesn't suffer, but you might not realize that you're overstressing the aircraft and the aircraft structure. And then what happened or could happen is one day out of the blue, the aircraft might be operating on this green area. And because it was overstressed, then you can have a structural damage. So it's very important that we have the aircraft correctly weighed within the limits established by the manufacturer. And more importantly, that when we fly between this range that we avoid overstress. Okay, so that's the implication. So now that we have covered that, let me then tell you the first thing about what we need to be sure before we fly. Before we fly, we need to be sure that the aircraft is between the aircraft weight limitations. And how we achieve that? Well, I'm going to take the advantage to provide you with an example. And in that example, we're going to also cover some of the some of the basic elements related with weight. All right, let me share this here with you guys. All right. Sorry for the delay, but this is getting a little bit annoying here. All right, so what we're going to do now is, let me show you some of the concepts. All right, so the first thing we need to understand is where the aircraft weight limitations, right? So where we find them. So let me go first and to show you where you can find these. And I'm going to use the Cessna 172R POH. So in that case, what we're going to look is here. Where's my, great. All right, here, sorry about that. So on the 172R, let me know if you can see the screen. What we'll see here is on the general section, on the first part, specifications, you will see a couple of things. It will tell you what is the standard empty weight. I'm going to explain that in a few seconds what it is. And then it's going to explain, tell us how much is the maximum ramp weight, in this case, 2,457, how much is the maximum takeoff weight, how much is the maximum landing weight, and how much is the standard empty weight and the useful load. So let me explain that to you with an example, all these concepts, and I think you will get it. So now you know where we get these weights, and then there is a section on the manual also about weight and balance that has more about this, right? So what we're going to be doing is going over an example and this. So basic empty weight, now you know where I got it. I got it from the POH. It says now 172R, it says that it's 1,639 pounds. And the basic empty weight is no other thing than the weight of the aircraft, structure, the engine, wings, all that, right? Wheels, plus unusable fuel and unusable oil. Remember, unusable fuel and unusable oil, there is some fuel in the system that you cannot use, but it's on the fuel lines and so forth, and the same with the, with the engine. Okay, so that's our empty weight, correct? So then we can have something that we call, the next concept we call is payload. And payload is the amount of either passengers, bags, or cargo that you can put in an aircraft, right? So in this case, I'm going to put, for an example, I'm going to put passenger one will have 150 pounds, passenger two will be 200. If you add these two, we have 350 pounds in the front. Then I said I have two passengers on the back, and they both total weight 250, and we have 50 on the baggage area, right? So if we add our empty weight plus our payload, it gives us our zero fuel weight of 2,289. Now, this concept probably you're going to see more on the commercial and the larger airplanes. I'm just putting it here for illustration because typically we always have some fuel on the aircraft. But here what we're telling is the concept I want to bring to you is that you always are going to be doing a trade-off between how much fuel you can put and how much payload you can take, right? So in this case, if I have, I have 2,289 pounds before I put any fuels, I know, right, that the maximum takeoff weight from the table we saw before is 2,450. So I know that I can carry 161 pounds of fuel. But now you're going to tell Manolo, but fuel, it comes in gallons. Okay, so write these down. 1 gallon of fuel is equivalent to 6 pounds. So if we divide these by 6 pounds, it's going to give us that we can carry maximum, if we want to carry all this payload, 26.83 pounds, gallons. So in this case, I'm going to assume that we're going to put 25 gallons. So 25 gallons multiplied by 6 is going to give us the actual ram weight, which is the zero fuel weight plus fuel. And then if we subtract the taxi that we need for taxi out, then it will give us the maximum takeoff weight. So here, as you can see, the first check I'm doing is if I'm between limits or not to the maximum weight. So clearly we're less, right? Because we're less both for the ram weight, which is 2,457, we are at 2,439, so we're good there. And then we're also good on the takeoff weight. All right, cool. Then the next question is going to be, hey, Manolo, how much will we have when we land? All right, when we land, well, we need to calculate how much fuel we're going to consume. So in this case, let's say that we did our flight planning and all that, and we're expecting to consume around 15 gallons. So again, we multiply 15 gallons by 6. That means that we're going to lose 90 pounds on weight. When we land, we should land at 2,342 pounds. Now, for the Cessna 172 in this case, that's not an issue. And the reason is because the 172 doesn't have, maximum landing weight is the same than maximum takeoff weight. As you progress in your career as a pilot, you will realize that other aircraft, that is not the case. This is why when let's say you're flying a 787 out of Hong Kong to Dallas and you take off and you need to return back to the airport for whatever reason, let's say emergency or medical or whatever, that's the main reason why you need to dump fuel, or you have to burn the fuel, and people spend hours burning fuel because the aircraft has a maximum landing weight limitation that is not the same than the maximum takeoff weight. Any questions with that? All right, cool. Now, the last concept I want to cover here, right, is the useful load. Useful load is none other than the maximum takeoff weight divided by the basic empty weight. And again, this is a good concept to have because this is what you have to play with, either fuel or payload. So in this case, in the Cessna, in this example, it's going to be 818 pounds which you can use for either fuel and passengers, as I said. One item I want to discuss before we leave. When you see the POH, you will see that they give you a generic but basic empty weight. And then you will see that the POH says something like your airplane. And you figure out, what is my airplane? It's like this way is not the same. Well, it's not the same, right? All the rest of the things typically are the same, but the basic operative weight is not going to be the same. And this is one reason. Let's say you're flying a Cessna 172 from 1978, like a 172N. Remember, this aircraft had some issues with the engines. Now, a lot of people did a STC for the 180 horsepower. Now, that probably is heavier, made some difference to the aircraft, how it weighs and so forth. So, or let's say now you put the new, GTN 750, 650, whatever avionics you like. All these can change the basic empty weight of an aircraft. So this is a generic exercise. So you need to use the specific empty weight for your aircraft, and that is going to be as part of the documents that have to be in the aircraft. Remember your airworthiness, your registration, operating, weight and balance, all that has to be at the aircraft. So as you do your weight and balance, especially you need to use the operating empty weight that you have on specific for your airplane that should have been signed by a mechanic that weighted the aircraft. Okay, any questions on that? Okay, cool. All right, so let's now that we have understood all this, and before we start getting into the calculations for weight and balance, let's understand one part is, okay, you are between limits and weight. Now let's see. The other part is that you need to be between, the balance have to be between limits as well. But before we go into that calculation, as I said, let's understand what implications the center of gravity has, or this center of gravity moving in this framework has with performance. Okay, so give me one sec while I set up this quickly. All right. All right. So now we're going to understand 3 is what is the impact of balance on performance, right? So for that, I'm going to paint this beautiful airplane. Okay. And I'm going to paint that you have a forward limit where the center of gravity can be by design, correct? And an after limit, that is this red, where the center of gravity can be, in order to avoid the situation we saw at the video initially. And then here, this is our center of gravity. Remember, center of gravity is none other than when you imagine that you can put that item, and that's the item is the point where all the forces are in equilibrium, right? And let's assume if you have imaginary string and you put the aircraft, is where that aircraft will, find their equilibrium, right? So that's our center of gravity. Typically, physically in physics, center of gravity is something like that, very similar to the BMW. It's the same. The only thing is colors are different. BMW same logo. And then we can extend this concept here quickly. So what I'm doing this here is for a reason. So let me explain to you what happened when we have the center of gravity a little bit move forward, right? Move forward. So what is going to happen with center of gravity is closer to the forward limit, to this limit here, what is going to happen? The aircraft is going to have a nose down tendency. So in order to compensate for that, right now, then the tail needs to produce a higher negative lift component in order to make the nose goes up. And then in that process, what happened is the wing, our wing here, as we studied before, what is going to happen is going to have a higher angle of attack. And if it has a higher angle of attack or a higher alpha, what is going to happen is we're going to create more drag. And as you remember, if we create more drag, then a couple of things are going to happen. So let me start making these more organized. All right, so we're going to assume that the CG is forward. That's what we're discussing, right? So if you have a higher angle of attack and you have more drag, what is going to happen is you're going to affect your fuel burn. And if you have a fuel burn with more drag, what is going to happen? Well, this guy is going to be higher, right? Then if you have a higher fuel burn, right? Let me do fuel burn here. If you have a higher fuel burn, let me see if I can close this. All right, if you have a higher fuel burn, what's going to happen with range? Well, your range is going to be, you got it, it's going to be lower, to be negative, right? Now, what happened with your stall recovery? Well, with stall recovery, you already are coming with a natural nose down attitude, then it's going to be easier, right? And then what happened with landing flares, right? Landing flare. Well, if you're coming now nose down, it's going to be a little bit harder because you now need to kind of pull the jaw back to kind of do the flare. So it's going to be harder here. And then what happened with the stability? Well, we already talked about this, right, on the lessons, flight principles. If the center of gravity is ahead of the center of lift, then the aircraft is going to be more stable. Now, what happened if the center of gravity moved backward, so aft? All right, so then the opposite happened. If you are, what is going to happen when you have a nose center of gravity close to the back part, right, of close to the aft limit, then the aircraft is going to have a nose down attitude. Therefore, that force on the tail is going to be smaller, which will make the angle to fly at a lower angle of attack. And if you have a lower angle of attack, you're going to have lower induced drag, right? Remember, less drag. And if you have less drag, then your fuel burn is going to be better, less fuel burn. If you have a less fuel burn, that means you can fly longer, right? Better range. Now, what happened with stall recovery? Well, it's totally opposite, right? Because now you are flying with a nose up attitude, and then if you want to recover now, you need to push forward more in general, and then this will be harder here, right? Harder. And then during flare, okay, we already come natural with a high nose up. It should be easier, correct? And then last but not least, we cover about stability on the pass as well. If it's aft, it will become less stable, right? And then as we saw in the video, if you go after this limit here and that thing shift way, way back, then something similar to what we saw in the video will happen, okay? So any questions with this? Okay, cool. Now let's start talking about how we do weight and balance and some of the terms we use during weight and balance. Ready for this? All right, let's go and do it. I'm sorry for these messages coming in. Okay, and so how we'll do this? Let me share quickly the POH again. And the POH, it has a specific section on weight and balance. Is in chapter section 6. So this section is all dedicated to weight and balance, okay, and equipment list. So let's go there. Okay, so let's start talking about some concepts here. Right? This is our Cessna 172. You can see here the first concept I want to talk about is the datum. I don't know if I'm pronouncing it correctly, but just imagine a fulcrum, right? A fulcrum. A fulcrum is a point where you should probably find equilibrium. And then typically we always measure distances from that fulcrum to whatever the loads are. So just imagine the datum is kind of that place, that reference place we measure. Some aircraft might have their engineers decide to use the datum or reference point from the front of the end here, I mean the airplane here on the nose. But in the Cessna 172 is somewhere here close to the firewall, right? And then that's where we use to measure all the distances where the items are, and that distance is what we call arm. So for example, you can see here is saying 0 to 50, 0 to 100, right? So everything that is measured from that datum to the back, in this case, it's going to be positive, as you can see here, 0 to 50, and everything in this case that is measured behind this reference point is going to be negative. If the datum is on the front, all the numbers are going to be positive, and you're not going to have anything behind because there is no aircraft structure behind the prop, right? All right, so why that is important? Well, because items on the aircraft are located in different distances compared to the datum, right? And they're here. They're going to call that an station, right? So let me go back to that quickly before we start doing that math. And so the station, for example, on the Cessna 172, they're telling you that passengers on the front are around 37 inches from the datum, or that's arm, they call it stations too, right? So that is where in average a pilot will sit. And just note that we have two numbers here, 34 and 46. And that's because these seats move forward and backward because they are adjustable. Like if I'm a taller pilot, right, I need to probably push this seat back in order to be comfortable. If I'm a shorter pilot, which I am, I'm very short, then I will put it all the way close to that 34. And so, but then that's, we need to pay attention. We're doing the math, but it's around 37 inches, right? Now, we know that from the datum to the rear passenger seat is 73 inches and so forth. As you can see here, this one doesn't have an asterisk, it's only 73, and guess why? Well, this seat is all bolted, it doesn't move, right? And then the same happen with the baggage area. They're using an average because you can have different places, and the same for the baggage area too. Now, a point here that I want to do is just read this note, and it says usable fuel CG arm for integral tank is located at station 48. So somewhere between the pilots and the rear passenger is 48. That's approximately where the fuel tank's station or arm is. Okay. Any questions? All right, cool. So how we use this for weight and balance? All right, so let me go back to my example we were using before. And in that example, now I'm going to uncover some cells that I have here that I didn't want you to show you, okay? Not to confuse you, but I have kind of put all this together here. So in the Cessna 172, right, we already kind of got our weight from our previous exercise. We know where we're doing limit and so forth. Now the question is, okay, how we calculate weight and balance? Okay, so it's very simple. Typically, what we need to do is calculate all the moments associated with the weights that we're going to carry. That's another way to say that, for example, the aircraft already have a moment because we know that, right? We know it's empty weight. It has an arm, which in this case we know is 39.3, and that gives you a moment of 64.4. And remember that a moment mathematically is not all other than the product of the weight by the arm. So if you multiply your 1,639 pounds by 39.3, you're going to get 64,400. Now the question is, well, Manolo, that doesn't look like 64.4 you have there. And the reason for this is that the manufacturers typically divide these numbers by 1,000 and thus or 100, and that is what we call a reference unit. Yeah. So in this case, they want to make the number more manageable, so they divide it by 1,000, and that's how it gives us 64.4. It's only a way to kind of make it more manageable, right? So if you understand that logic, then you understand that center of gravity is no other than the sum of the weight of the sum of the moment divided by the weight, that's center of gravity. So that's, we always can find the center of gravity if we add the moment divided by the weight. So that's what you can do here, right? 64,400, if you divide it by 1639, it gives you 39.3. Okay, so, and that's what we're going to do later on. So we keep doing our multiplication, right? We know that it's 350 pounds that we have in the front, multiplied by the 37 here, it gives us 13,000. We again use the reference, use the reference to divide that and give us 13. We know from the previous example that we are carrying 250 pounds for both passengers in the back. We know the arm is going to be 73. Sorry, let me change this to 73. 73, that's 18,300. Again, using the reference is 18.3. And then we're only going to carry 50 on area 90, on the baggage area. So 50 multiplied by the arm give us 4.8. So now we can add our total weight, 2,289, correction, our 100,400 or divided by 2,289 gives us a zero fuel weight center of gravity of 43.8. But now we need to see if add the fuel, correct? So if we add the fuel, we already know from our previous example, we have 25 gallons and multiplied by 6 give us 150 pounds. As I told you before, from that note on the POH, we know that the station for the fuel is 48 inches from the datum. Now, if we multiply 150 by 48, it gives us 7.2 or 7,200. And now if we add our previous moment plus the fuel moment, now we're ready to calculate our center of gravity before takeoff. And we calculate it to be 44.1. So now how do we know that we are between limits? Okay, so what we do here is we go back to our POH. And we're going to use this table called this table called airplane CG locations, right? So what they're telling us, we have calculated that we're at 44.1. So let me see if we can draw something here. So let's say 44.1, and we know our total weight 2,432. Let's call it somewhere around there, right? And then 2000. Let me move here quickly. Let's call it like that, right? This is 2000. Yeah, around there. So that's our center of gravity. We're very close to maximum takeoff weight, but we're between limits. Okay, now the next question is, okay, that's super cool, Manolo. Now, how do we know that we are between limits when we landed? And that's a very valid question. So then we already did that math before for the fuel consumption and the weight. So we know by a fact that we're going to land within limits. But now we need to check if we are going to land balanced. And then we know that from our example before, we're going to consume 15 gallons during this flight. That's equivalent to a reduction of 90 pounds, right? And we know that the station for the fuel is 48. That gives us a change of momentum around 4,300 or 4.3 if we use the reference unit. Now we subtract, right, that 4.3 from our takeoff momentum. It gives us 102.9, and we subtract, the 90 pounds from the weight. And if we divide momentum by weight, we will get our new center of gravity. And this center of gravity is now going to tell us that we are at 43.9. That's our center of gravity position now. Again, so we'll go back to our table and then we'll look for that point. So, okay, so let me go and do a notation here. So this is 2000, 2050, so 30, let's call it like here, just for the sake. So somewhere here, and we know now that we are at 43.9, let's call it 44. So we should be around here. Okay, around there. Correction. I make a mistake here. Give me 1 sec. So that's for 44. That's for takeoff. Now for landing, what we're going to do is we're going to land at 2,342, which is, this is 200, so let's call it here, and like that. And then let me delete this guy here, and that will be, okay. And then let me do the previous one, that is 44.1. So we're around here, and then we were here. Okay. So as you can see, we kind of move this way down on center of gravity. And that can give you a good indication if we continue burning fuel, how much are going to go down, right? Until we get to our zero fuel. Okay. So sorry about that. I might need to improve this a little bit better, maybe put the points to kind of make it clear and not confusing. Any feedback on that will be appreciated. Okay, so what I have explained here now is what we call the computational or method, right? So we went through the math of every element and then we came to the method. You will find another method and it's called the graph method. If you go to the POH, you will find that method as well. But for sake of saving us going back and forth, what I have done is I have put an example here on my Excel file as well. So this is our weight and balance on the graph. So as you can see here, right? Let me know if you can see the screen. I have the same weights than before, right? But now what the engineers at Cessna have done on this graph is they have said, hey, Manolo, don't worry about calculating weight by arm. We just put the weight and we have done that calculation for you and we have put it on these lines that you can use. So for example, right, we know that our empty weight is 1639 and we know our moment is 64.4 using the reference, right, numbers divided by 1,000. Now I know 350, right? That's the same amount that we were using before. So what I'm going to go is go all this line up, 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 up to 350, sorry, around 350 here, and it's going to give me somewhere around 13, right? 13. So 1, 2, yeah, 13 around here, 13. Yeah, 13. Yeah, so 350 kind of on the half will go and then 13. Now let's assume for the passengers in the back, so it will go 250, so 250 all the way here to 250, and then that will give us down around 20. Sorry, that's around there, around, it's around 18, 20. So yeah, 18 there. And then we can put it like that. Now, as you can see, you can continue this and it's going to give you an approximation. And then then the only difference is if you use this method, right? Then you need to use, instead of our center of gravity graph envelope we used before, then you need to use this one, you see, this one. And then you're going to use whatever that number gave you and look into the envelope here. Me, particularly, I'm more of a mathematical person. I prefer the first method first because I can check the math and I'm not guessing with this curve. And then I quickly go back to, the graph and look at where the center of gravity is, right? But it's up to you. Then last but not, well, it's not only up to you, it will also depend on what aircraft is using, and that's a good segue for my next topic, because an aircraft, I mean, the Cessna provide you the ability to calculate these two, and the computational, you might need to do a little bit of rear engineering for the empty weight, but you should be able to figure out the weight and balance using the computational and the graph method. But maybe in other cases, you don't have that, right? So that's a good segue for the other type of weight and balance calculation that you can see. And that will be the table method. And the table method is a version of these graph methods that we showed you before. But what the engineers are doing is they're not plotting in a table, in a graph. They're leaving you the data on a table format that you can go and get the data from. So let me go to my weight and balance chapter. Sorry, guys, I forgot to set up this. I think it's let me go back to the indexivity index because I think it's chapter 10. Yeah, so let's go to 10. Okay, cool, here. Okay, so again, if you read the PHAC chapter 10, as I indicated, you're probably familiar. I covered the computational method. We went over the graph method. And then last but not least is the graph method. So as I told you here, what they're doing is they're not providing you the data in a graph, but if you plot these numbers here, it's the same than the graph. But if you ask me, if I don't use the computational, I think I will like this one better. You will see this a lot on the Beechcraft aircraft. So here, what you will do is look at your, for example, on fuel, you will use 44, then they give you the weight, and then automatically they give you the momentum. So what you do is keep doing all these and checking your weights, what the momentums are, and you will come here and add all the momentum and then find, your limits and your center of gravity and limits, and then you can compare here quickly what it is. So this method, if you ask me, I like this too because it's more numerical and I can cross-check quickly what it is. The curve may be a little bit imperfect in terms of, you see, I have to do some manipulations and look into, okay, it might be 18.5, might be 19. So anyhow, it's always good to kind of have buffers as well on this, that you don't want to be kind of getting too close or to the back or to forward. So, pay attention as you go through these. Any questions on the three methods and terms used for weight and balance? Let me check here my notes to see if I miss anything and I'm not shortchanging you guys. So we talk about moment, we talk about center of gravity, we talk about CGs and so forth. We talk about the combinational method, we talk about the graphic method and the table method. Cool, okay. Now, and I showed you three examples. Now, let's go on to the last topic of the lesson, which is how we calculate shift in the center of gravity and how that affects this. So let me bring my presentation again. That's probably the best way to do it. Okay, so in this case, right, the first thing we need to learn is that you can use this formula. Again, I'm very numerical. And this formula is telling you how you can find a CG after you shift either the momentum or the weight. So as you can see, M1 and W1 is none other than your current center of gravity. Remember, we talked about that before. Momentum divided by weight is center of gravity. And then you will add to both sides of the equation your delta in momentum and your delta in weight. Now, there are a couple of conventions that you need to follow if you want to use this formula. The first is that a weight always create an addition of moment, right? Moment change. And if you remove weight, then you're reducing momentum. And that's easy because remember, moment is arm multiplied by weight. So if you are adding weight, then you're creating more momentum. If you're removing weight, you're removing momentum. That's straightforward. Now, the second is that if you have the shift moving rearward, remember, we're always measuring things from the datum, right? So if you move forward, you move back, that means you're adding, you're increasing the distance from the datum. So every time that we move rearward, you have a positive moment change. If you're moving the other direction, you're getting closer to the datum, therefore you have a negative momentum change, okay? And if you don't have a change in, if you're not moving weight between one station or another or arm, then the only thing you're doing there is you only have changes in the on the moment. Okay, I need to review this again. Let me. Okay, so let's go with example one. So let's say our airplane took off with 6,230 pounds, and the center of gravity before we took off it was for the entire aircraft is 79 inches. So then the question is, what is the location of the CG after 50 pounds or 15 gallons, right? And then they say 300 pounds, you know why, right? 50 gallons multiplied by 6 is 300, has been consumed from station 87. So that's very similar to the things we did before in the Excel file, but now we're going to use this formula. So we know today, right, that momentum is 6,230 pounds multiplied by the station where that, or the arm where the CG is, which is 79, and then we divide that by the weight. So this equation is our center of gravity. It should be equal to that 79, right? And then since we are losing weight, right? We're losing 300 pounds at station 87. There's going to be a change of momentum, and we're also losing weight because we're losing weight due to the fuel. So now this is a new center of gravity, 78.6. Okay. So any questions with that one? Cool. And this one is a little bit more complex. And then this one is telling us that if an aircraft take off with 3,000 pounds and the CG is at station 60, or is the same to say 60 inches from the datum. And then they said that since takeoff, 25 gallons or 150 pounds of fuel has been consumed, and the fuel cell CG is at station 65. And then they tell us that a guy decided to move, right? A passenger moved from a 200-pound passenger moved from station 50 to station 90. Then, find the resulting CG. So here we have our initial, right? Our initial weight is our initial momentum is 3,000 multiplied by 60. And here we have our initial weight, 3,000. Then we know now that we are consuming some fuel, and that's going to change momentum. So we're going to subtract, the 150 150 by the location of the fuel cell, that is in this case 65. And then noted, as I told you before, now we are adding. Why are we adding? Well, because that person is moving rearward on the axis, right? Just imagine is moving from one station from station 50 to station 90. So we need to add that more because it's going to add more momentum. So for that, then we add the weight. We know that person is 200, and now we need to find the shift on that distance, which is 90 to 50. Now, just note that because this person is not changing weight, because the person is not going to change weight on flight, the only thing that we put on the bottom of the formula is the fuel burn lost weight that we saw. So when we do all that math, the new CG is 62.54 inches. Now, look, there are ways, it's up to you if you want to use that formula. Sometimes I prefer to use, kind of rerun the numbers quickly myself. If you have the E6B, that's pretty easy to do as well. We can go over that example if you want to, how I will, how you can do it without using this formula. But this is kind of how the FAA recommends on the PHAC. But there are other ways that we can achieve that. Might take a little bit longer, but if you feel comfortable doing that way and it's more understandable, then do it. I can run you through that math. So, well, that's the end of our lesson today. Let me recap that we cover everything. We cover the effect of weight in aircraft performance and airplane structure. We cover the impact of balance on performance. We cover the 3 methods, how to calculate weight and balance. We also cover the main terms you will find during your weight. And then last but not least, we cover how we find if we're balanced or not, and then how we can find changes on center of gravity if we have a fuel burn consumption, or if some loads change during flight. And again, this is very important. I think the things I want to do for closing remarks here is, number one, remember you always have to have your weight between limits. Weight within limits will satisfy that you're not flying the aircraft out of that envelope, right? That we discussed, and then that you're, more importantly, that your aircraft is balanced. And if it's balanced, you're going to guarantee that the aircraft is going to fly as it was designed, right? You don't want to be in a situation that the aircraft is overweight and out of balance because the aircraft clearly was not defined to fly that way. And you don't want to become a test pilot, right? That already was done by Cessna, and these are the numbers, or the manufacturer, the aircraft you're using, that these are the numbers they provide you and the tables they provide you to guarantee that you are going to fly safely and efficiently. So with that, I hopefully you enjoyed this lesson, and I will see you next for our next lesson, that is going to be flight planning. And for that lesson, I'm going to be sending you an email with the lesson plan and the activities I want you to complete before we meet again. All right, thank you, have fun, and keep flying. See you soon, bye.